Everyone. Welcome to the third Young Ceramist Network webinar. At the same time, the first webinar of this year. I am Yasmin from Turkey. I have a bachelor degree in ceramic engineering, master and PhD degree material science engineering. Some of my topics is about studying biomaterials, defense materials, silicon nitride materials, high technology ceramics. I have been member of ASERS 2005. First of all, I would like to give Maria an opportunity for a little presentation about Young Ceramist Network.
Okay, thank you, Yasmin. Well, I will present a little bit what is the YCN. The YCN were born in the European Ceramic Society, and the activities we are promoting are sponsored by the Journal of ISER Trust. This trust is an agreement between the Elsevier, the editorial of the journal, and ISER. This agreement, which is doing, is come back part of the benefits of the journal to ISER, and ISER decided to invest in young people. That is the committee. The current committee is composed by Nicolas Somers, Antonia Ressler, Laura Tianen, Erka Framberg, and myself. We are coordinated by Veronique Huart, and we are supervised by Andrat Koyan. Well, we are trying to promote professional events, to promote contacts and links between you, and also you can exchange ideas. We are trying also to give you information about funding and job opportunities and promote the research and innovation. You can find the YCN in our website. You can see here a map with all the institutions of our members, and also the contact of Facebook and LinkedIn, and also about our newsletter, which is important in our newsletter, is our research in spot and industry in spot. There, the members can share the projects or the ideas in which they are working. That is our social media. You can find us in LinkedIn with more than 650 members, in Facebook with more of 870 members, and we have recently arrived to Twitter and Instagram. That is one of our current projects, the series of webinars. The first one was with Professor Richard Todd, and the second one was with companies, and the topic was sustainability. We have another important project, is the special issue in Open Ceramics, Young Ceramics in the Spotlight. And you are on time if you want to submit a paper up to the 31st of January. We will give a best paper award of 1,000 euros. Finally, other of the projects we are developing is the third photo contest. The photo contest, the deadline was already finished in December. 21 micrographs have been submitted, and we will give a prize to the best micrograph. So if you like the project of the YCN, you can join us in social media. I give you the word, Jasmine.
First one is done by Tatarko. I will give some information about him. He has a master degree from Košice Technical University, Department of Metallurgy, and PhD degree as well, is the same one. Between 2013, 11 and 13, he has studied on postdoctoral studies with the Marie Curie fellow at the Brighton Fractured Group. And then he worked in SAS in Košice. After this, he made researches at the University of Queen and Mary in England. He had job as an expert researcher at the Department of Structural Ceramic in Slovak Academy of Sciences in 2015. Since now, he's been going to at the same department, ceramic in Slovak Academy of Science. Yeah, that is. He will make his presentation now. Hi, Peter.
Hello. Thank you, Yasmin, for a nice introduction. I'm just checking. Yeah. Hello. So I hope everyone can see my presentation now. Yeah. Thanks very much for the nice introduction. So first of all, I would like to say thank you very much to Young Ceramics Network, and I really greatly appreciate this chance to have this presentation within their webinar series, and I greatly support all their activities. So thank you very much. It's my great pleasure to be with all of you here today. So for today's seminar or webinar, I would like to speak about the joining of silicon carbide advanced ceramics. And first of all, I need to say, because I want to show you here some summary of all the results which me and my colleagues we obtained in the last 5 years. So at the beginning, I must really acknowledge all the support and all the contribution from my co-authors, which you can see here from Queen Mary University of London, and also from Politecnico di Torino in Italy, and also from my colleagues from Institute of Physical Materials in Brno in Czech Republic. So first of all, and at the beginning, I'd like to explain what I mean by saying silicon carbide advanced ceramics. So as some of you may know, carbon fiber reinforced silicon carbide and silicon carbide fiber reinforced silicon carbide, these we called ceramic matrix composites, and these ultralight materials are very important and are being very useful for aerospace and nuclear applications. Here you can see some examples. So for example, these empty aerospace, this is the body flap for re-entry vehicles, or this can be used as a parts for combustion chamber, or these materials are also very important for nuclear applications, and where they can replace zirconium-based alloys. So we can nowadays say that these materials are being more and more used in for these applications, and there have been really great research and many works focused on the improvement of the properties of these materials. But one issue still remains there, and this issue is to develop a cheap and user-friendly and reliable joining technique to combine all these small parts into such a complex structures. And me and my co-authors, we tried our best to contribute to this field in the last couple of years, and we were also involved together in one European project called ADMACOM. It was the Factory of the Future project within FP7, and the coordinator of the project was Professor Monica Ferraris from Politecnico di Torino. And you can see all the partners here, and I just would like to point out that among the others, we also had 2 industrial partners, MT Aerospace and Airbus Group Innovations. So our aim of the project was to develop new joining technologies for aerospace components. So projects define several different approaches. Here you can see, for example, the brazing of the alloys, or using transient liquid phase bonding, also electric current assisted processing. And then the other 2 are mainly focused on the processing and modification of surfaces before joining. So all these activities were focused, because here I'm just showing you the same example as on the slide before, because these are great examples of one of our project partners, MT Aerospace. Here you can see the body flap. And the idea of all the project and why we started working on this important field was that this empty aerospace, this on the body flap, you can see here that they were using either mechanical joints, so here you can see several screws, or they were using in situ joining by CVI technique, because these materials were produced by carbon vapor infiltration, and they were using in situ joining technique. So our aim was to come up with some alternatives to suggest a new joining techniques for the industrial partner. Apart from that, this is in the board, you can see. So my main topic I decided for today's seminar it's going to be on spark plasma sintering joining, or if you want, it's electric current assisted processing. So we had to start on this in a small scale, of course. So here is one example of the materials which was supplied by MT Aerospace. And one important feature which I would like to point out here, these materials are always covered by CVD silicon carbide layer. So here you can see the top view, this is the backscatter image, and you can see the side. So you can see very uniform light gray phase, which is CVD silicon carbide. Just to see the difference, here you can see the uncoated materials, and you can see this light gray phase is the silicon carbide from the matrix, but you cannot see such a uniform layer of the CVD silicon carbide. The reason why they were using this material is just because of having a better oxidation protection. So because these materials are always covered by CVD silicon carbide, that's why instead of our aim was to join carbon fiber reinforced silicon carbide, we started optimizing our joining process using the monolithic beta silicon carbide produced by CVD, because at the end is the same interface which comes into the contact when you want to make a joint. There were some requirements we needed to consider before developing a new joining process, and we needed to use temperature and time as low as possible. We preferred solid state diffusion bonding. We didn't want to have any liquid phase formation during the joining because we wanted to avoid shrinkage of the filler to not produce residual stresses in the joint. And of course, we didn't want any strong reaction between the filler and the matrix, and of course, no decomposition of the filler. These all 5 points were very important for us because we wanted to, at the end, we wanted to avoid any damage to fibers or protective coating on CMCs. And for this process, we use electric current assisted processes, spark plasma sintering. This is my main topic for today's webinar. So we use a standard SPS spark plasma sintering machine, which you can see here. For those who don't know, this machine just works because you have 2 graphite punches, which are connected to the electrodes, and they are connected to pulse DC power supply. And in case you have insulating sample, so electric current goes through the graphite die, graphite punch and graphite die, and then heats up the sample indirectly. In case you have a conductive sample, then you have a combination of both direct heating and indirect heating. This, for today's presentation, I will call these processes as a SPS joining. But you can also skip using the graphite die, and then you only use 2 punches, and then you don't have any die in here, so the current has no other option, just go and flow through the sample. And this, of course, the sample needs to be conductive. And for this kind of technique, I will be calling flash SPS joining. So I can say that my presentation today will be consisting of 2 parts. One will be on the SPS joining, and one on flash SPS joining. So let me start with the first one. Okay. So as I said, it all started with CVD silicon carbide. So basically here you can see what we had. We've got pure CVD silicon carbide material. We've got 2 blocks, and it was quite simple. We put 1 block on another. We put in the graphite dyes, and then we put it in the SPS, and we applied temperature and a little bit of pressure, and we got a joint. As the joining materials we were using, in the first case, we call it direct bonding. So it means we didn't use any interlayer. So it seems there was nothing in here. We only compare 2 surfaces, which in one case, the surface of CVD silicon carbide was polished. In other case, it was unpolished. And then we just compare the effect of the surface roughness on the joining. In other two cases, we used titanium-based, it was pure titanium and titanium, aluminum, vanadium foils. So we inserted this foil in between these two parts of silicon carbide, and then we use it as an interlayer. In the last case, we also use the max phase, but it all has some reason which I want to now explain you and convince you that it was a good option to go to. So I forgot to mention here, so after joining, we cut the samples and then we performed some mechanical testing, as you can see here. So first of all, just you can see this is the bending strength of the reference unjoined sample. So it's a pure monolithic beta CVD silicon carbide. The strength was around 220 megapascals. And then when we tested the joint sample, this is the direct bonding unpolished sample. This is direct bonding polished sample. So you can see that especially for the polished sample, we got quite a good strength. It reached almost the initial strength of the joint of the reference material. And you can see for joining, we used 50 megapascal and 2000 in this case, and 1900 in the second case. Especially, we got very pure bending strength performance for this unpolished sample. The reason was very simple. If you look here on the polished surface, on the tensile surface, here you can see the joint. And if you look closer at a higher magnification, you can see these voids at the interfaces. Because it's just logical, because you don't have the polished surface, so you have a very high surface roughness. So basically, even though we use 2000 degrees C, the joining conditions were not enough to allow diffusion, solid state diffusion, and to fill up these voids. In case of the polished sample, we could not even find the interface. So that's why I'm not showing it here. But what I can show is the fracture surfaces after the test. Here you can see the unpolished fracture surface. So you can see it's very smooth. Basically, it's just delaminated where the initial joint was. In case of the polished surface, however, you can see we got really standard, typical fracture surface of silicon carbide, which it suggests that the joint was very strong, and we did not get any problem and almost reached the initial strength of the reference material. So the problem was the temperature. These processes require very, very high temperature. So we wanted to reduce the temperature, and we used titanium and titanium aluminum vanadium foils. You can see we could lower the temperature to 1700 for titanium or 1650 for titanium aluminum vanadium. And especially for the titanium aluminum vanadium, we got very nice strength which reached the reference unjoined material. These results were very positive, and we were very happy about that. Unfortunately, when we look at the cross sections of these joints, there were two important issues we found. And the first was a significant shrinkage of the filler. Here you can see we used titanium interlayer, which with a thickness of 30 micrometers, and we ended up with the interlayer about 15 microns. In this case, aluminum vanadium, we use also 130 micrometers, and especially for the first case, you see again almost 50% shrinkage. So it was very, very dangerous because it can produce the high residual stresses in your material, and that's why it explains a lower strength than in the case of 30 micrometer foil. So, and the second important issue, which I would like to point out, you can notice here that the alloy was very reactive. You can see all these like a nail-like structure. So it all can damage either carbon fibers in the composite or the protective silicon carbide layer. So that's why we needed something else. One important point, when we did the XRD after the joining, we found, of course, silicon carbide from the matrix, but we found the titanium silicon carbide, so-called max phase. So in other words, this joining I will go back. This joining interlayer was formed by max phase titanium silicon carbide. So the question was, why to use titanium at 1700 and then you end up with a max phase if you can use max phase directly as a joining filler? So that was our motivation to use max phase as the joining filler. So very briefly, we synthesized this max phase powder using microwave sintering, and you can see there are very typical impurities for these materials: titanium carbide and titanium silicides. We intentionally added some alumina because alumina helps you helps you sintering of this material and also helps oxidation protection to the material. So this powder was sintered by SPS at 1300. And what happened, it was very interesting. You can see here, this is the powder, initial powder, and this is after SPS sintering. Here, this graph, it's zoomed in of this graph. And what you can see, after SPS sintering, all these impurities, all these peaks referring to the impurities, they vanished. We didn't see any other titanium carbide and titanium silicides anymore. So it was very important for us because, in other words, we used for joining, we used pure max phase, of course, with some alumina, but as I explained before, we wanted alumina to be in there. Then we ground this material to around 100 micrometer, and then we inserted this foil, 100 micrometer foil between two silicon carbide, and then we use SPS, and at the same temperature as we synthesized and sintered this material. First, very clear and very nice results were when we looked at the cross section of this joint. You can see in this case we didn't have any shrinkage. We didn't have any. If you remember this nail-like structure, here there is nothing. So the interface was very clear, very smooth and very nice. So we were happy about that. So we could, if we zoomed in, we only found these are the alumina particles which we wanted to be, them to be there, and then the remaining was just the titanium silicon carbide. So from how the joint looked on the inside the SCM, we were quite happy with that. And then let's have a look how the joint mechanically performed. And you can see here that with the titanium silicon carbide, we got really almost the same strength again as we obtained for unjoined material. The important thing is, you look here, we started from 2000 degrees C and we lowered down the temperature up to 1300 degrees C, which is significant reduction. So in other words, we only use 1300 degrees C, but we retain the same strength of the materials, which is very important feature. That's why we wanted to also see how these joints, because of course, as I mentioned at the beginning, these joints were supposed to perform at a higher temperature and extreme environment. So we needed to know how these joints will perform at high temperature. And we did the same, you see, same preparation of the beams, and then we use high temperature bending strength in vacuum. And then when you see here, this red line, it shows the reference strength measured at the room temperature. And then you see 1000, and then 1100, 1200, and so on. You can see that at 1000, the strength of the joint is, so the temperature up to 1000 had no effect on the strength of the joint. Then the strength continuously linearly decreased with the increasing temperature. But the important fact is that from our project partner, from the industrial project partners, MT Aerospace, we knew that critical temperature for them was 1200. So you see that even at 1200, the strength retention was around 70%, which was quite okay. And we still had some room, some space to improve, because even at 1300, it was still around 40% of the strength of the initial joint. So it was quite good results, and we were quite happy with that. If you look just very briefly, just a few images of fracture surfaces, you can see at the room temperature, the sample failed outside the joining. Here you see the joining interlayer, and the sample failed outside the joining area. With the increasing temperature, here you see 1000, 1100, 1400, the interface, here you can see interface or the filler played more important role, and especially at a very high temperature, the filler was the weakest part of the joint. A very important fact was that because the tests were done in vacuum, so we didn't find any we didn't find any decomposition of the max phase because we didn't see any titanium carbide or silicides or any other impurities. You see here at 1400, the pattern looked exactly the same as at this joint sample, which was very good. If you look at these images, you can only see that typical damage at a high temperature, like microcavitation, microcracking. So that were the typical reasons for failing the sample, not the composition of the filler. So all of these made us believe that this material is promising to be used for carbon fiber reinforced silicon carbide. So now coming to the composite, which was our main priority. Here, as I mentioned, we got some samples from MT Aerospace from Germany, and then we used a very similar process as I described before. Just in this case, we use carbon fibers reinforced silicon carbide, and then we used the same temperature and all the same parameters like we used before. Here I would like to show you here, just to remind you that we have two. Okay. I just to remind you that we have two types of material. So one was coated. So you see here, it was fully coated from all sides by CVD silicon carbide layer, as I explained before. And then here you see the uncoated sample. So coming to the results, here is the cross section for the coated sample. So first thing was that we noticed that the foil, the interlayer, was really ductile, because you can see it conformed very well to the rough surface of the CMC. Another important thing, here you see the CVD silicon carbide coating, and this coating always has some cracks because of the thermal mismatch between coating and the matrix. So in our case, after joining, we actually filled up these cracks with our filler, and actually, in other words, we healed these cracks. You can see here the EDX mapping, so it was really the same, like titanium and silicon is depleted by silicon but enriched by titanium. So it's clearly seen that it's actually our joining filler to come in and heal the crack. This showed at the end a very promising, a very good result for strength and for the mechanical performance. Here I'm coming to the result for uncoated samples. In this case, we have actually not one interface only, but two interfaces. One interface was between silicon carbide matrix and our joining filler, and in the other case, between carbon fibers and joining filler. Especially in case of the interface between silicon carbide and the filler, there was exactly the same situation as in the case before. But in case of the carbon fibers, very important thing is we were worried about not damaging the carbon fibers, of course. But you can see here that these SCM images and also EDX analysis confirm that actually the filler reacted with carbon from the fibers and actually formed in situ silicon carbide reaction layer. Once this layer is formed, then it stops the further diffusion. So actually, you don't get the damage to the carbon fibers. Coming to the mechanical performance of these joints, here is the values. It's between 25 and 35. This was the value we got from the supplier from the MT Aerospace as a reference sample. You can see that when we used coated samples, then you can see that the strength of the joint was, this is apparent shear strength, I should say. And for these coated samples, we got the strength just right in this interval of the reference sample. In case of uncoated, the strength was a little bit lower, and we believe that we got this higher strength for this case just because, if you remember, as I said, this filler was better integrated with the matrix because it filled up the cracks and it healed up the cracks. So it was the filler was better integrated with the matrix. So that's how we explained this higher strength. If you look at the fracture surface, you can see no delamination, but the crack went from one part of the composite into the second one. So this suggests that the strong joint was very strong and stronger than the interlaminar shear strength of the material. So that was the results which at the beginning I called SPS joining. But I would like, because we were happy with that result, but as I mentioned at the beginning, it was indirect effect of the electric current. So we were always using the graphite dyes, and here is the picture. So we were using the graphite dye, so we heated up the sample indirectly. We wanted to actually explore a direct effect of the electric current. So that's why we wanted to go further and to understand the effect of electric current on joining performance. So that's why this is my second part of my talk, which I would like to try to explain how we developed this. What we did was quite simple. We put the sample, we wrapped the sample. There is always noise behind there. We wrap up the sample in the graphite felt. You see here is our sample, CVD silicon carbide coated carbon fiber reinforced silicon carbide, and we wrap up within the graphite felt. Then we put it in between two graphite punches in the SPS machine. Then we applied a little bit of pressure, and we applied the current. So what we were relying, why we use this felt? We were relying on the fact that at the beginning of process, we were relying on the fact that at the beginning of process, graphite felt has lower resistance than our samples. So the graphite felt will actually heat up first, then it preheat our sample, and then the resistance of the sample drops, and then of course the current goes through the sample and we can obtain the joint. That was our hypothesis, that was the idea, and we tried to explore, and I would like to now show you how we did that. So in our SPS machine, we could only control the power only by setting up the power limit. So what we did, we set up the power limit to 80%, and we interrupted the process after different times. So here 22 seconds, 19 and 12 seconds. So of course, the lower the time, the lower the heating power, and of course, the lower the current. So in all these three cases, we obtained joints. So after joining, the material could be cut, we could polish, and then look by SCN. But the problem was, if you see here, this is for the sample number 1, 2, and 3. Yeah, you see the power is decreasing. You can see very clearly that actually the power was so high that we actually decomposed the CVD silicon carbide matrix and the coating. You see here all these holes. Also in this case, it was a decomposition of the silicon carbide. So in other words, the power was really too high. In other words, the temperature inside was really extremely high. But what we also saw that with the decreasing power, here is the lowest, and here is the lowest lowest power, and you can see the composition is less significant than in this case. So we could see some clear effect of the heating power. Another issue we had that you can see here, titanium. Here is the joining interface, but titanium, we found titanium even at the places far away from the interfaces. So basically the titanium melted, and because these materials are porous, so it actually went everywhere. So it was really not successful result, but we could see clear effect of the power. So that's what we did then. We set up the power limit to 60%, and we keep almost the same time like in the case before. You can see here, in this case, we didn't see any decomposition of silicon carbide anymore, which was a good sign. On the other hand, the titanium foil, you see porous titanium foil, it was really again melted, and you see here far away from the interface. So it was still an issue, but we were sure that we are on a good track. So what we did then is we kept the same power limit, but we just reduced the time. So you see, we use only 7 seconds in this case. And you can see now, no melting of titanium, no decomposition of CVD silicon carbide. So basically, we got really nice joint. We don't see any significant reaction between the joining filler and the CVD silicon carbide coating. So it was very different than in the other case. So what happened if we compare the first sample with the heating power and the last sample with the lowest heating power, you can see the resistance of the sample in blue line, they actually no effect, yeah, it drops very, very similarly. But then the heating power for the sample number 1 with the highest heating power, you see it continuously increasing until around 7 kilowatts. But on the other hand, for the last sample, it just, you know, we dropped it here and it just fell down. So so our idea or our results showed that it works. You just need to stop or interrupt the process right in the right time. So if you interrupt your process once, the resistance drops and reaches the plateau, then it's just the right time to interrupt the process. So it was all fine. We wanted to see what is the composition, the chemical composition of the joint, but you can see clearly there is only titanium. You don't see any silicon or carbon diffuse into the layer. Truth be said, we also did EDX by TM, because this is on SCM. We did also by TM, and we found some very little concentration of silicon and titanium, silicon and carbon in the titanium, but basically the concentration of these two elements was not really enough to produce some phases, as it will happen later, which I show you. This was also confirmed by XRD results. You see only titanium, this is blue triangles, only titanium we found. So coming to the most important thing, of course we wanted to understand the temperature, because we knew what is the power, we knew we got a nice joint, but everyone's asked what is the temperature in there. So we inserted the thermocouple just right at the joining interface, you see here, and then we put it in the SPS as before. And you can clearly see here that the temperature, the maximum temperature we measured was below 1250. So it's much lower. The melting point of titanium is around 1560. So this is really below melting point. So the titanium could not melt, and the temperature was so low that it did not allow any diffusion of silicon or carbon into the titanium. You can see extremely heating rate. It's 9,000 degrees C per minute, or if you want, it's 150 degrees C per second. So it's extremely fast process, and that's why this diffusion of these two elements was delayed or hindered. Okay, I can skip that. So after join, of course, after understanding what is the temperature in there, what do you have in the joining area, you always need to know the strength, the mechanical performance of the joint. So we cut the sample right from the middle of the sample, and here you can see that we got apparent shear strength about 31.4 megapascal, which is very extremely high value, and we reached the value of the reference unjoined material. I will show very soon. I will show the comparison with the other process. Here is just the example of the fracture surfaces. You can see, because here I would like to point out the conformal behavior of titanium. For here, this layer, which was of course peeled off at some places, but you can see how it nicely conformed to the rough surface of CMCs. So this is very nice, nice results as well, and that's the reason, because it conformed very well. It got nice integration with the matrix. That's why we could get such a nice high apparent shear strength. So as a last part, very last part is the, of course, comparison with the standard SPS joining, because we set up here, we didn't use the graphite die, we set up a new process, we were playing with the heating power, extremely short period. So we somehow wanted to compare with the standard SPS process. So we did the same thing, but this time we use again the graphite die. And you can see we used the same temperature as we measured here. You remember here was about 1250. So we used the same temperature in here. We used no holding time, as it was not for the flash process, and we use also rapid cooling as for the flash process. The only difference was the heating rate, of course, because here is 100 degrees C a minute, which is standard heating rate for standard SPS process. If you remember, for flash SPS, it was 9,000 degrees C a minute. So significant difference. At the end, when we apply this kind of process, we didn't obtain any joint. So you see this is just the cross section of the delaminated form. So basically what happened, you got we tried to join, and then after joining, the CMCs fell apart, and only we got this delaminated titanium form. But we still could polish it. The polishing is not perfect, but doesn't matter. It shows what I want to see. What I want to show you is here the reaction layer. If we did, of course, EDX, and you can see this is titanium, and here you see silicon and carbon. So also by XRD and also EDX mapping on TM, we confirmed that there was a titanium carbide forming and titanium silicide. If you remember, for the flash joint process, the interface was clear, no diffusion, or let's say, I wouldn't call it no diffusion, but let's call it minimal diffusion, not enough to form additional phases. So if we wanted to get a similar joint using the standard SPS process, we had to increase the temperature to 1700, and we also had to apply some dwell time, and we also applied a cooling rate 100 degrees C a minute. When we use this, when we modify the standard SPS process, in that case, we got a joint. So you see no delamination, and we could test this joint. But if you look at the EDX mapping, you can see again, in the middle part of the joint, it's titanium carbide. You see carbon concentrated right in the middle. Then you see silicon in here. So you see titanium silicon, so it's titanium silicide. So as I showed before, it's not pure titanium as it was in the case of flash joining process. So here is one summary, and you see here, this is a reference unjoined sample. If you remember well, I said during my presentation that the values is between 25 and 35. This is reference from supplier. But if you use flash joining, only 7 seconds, we got interlayer, the metal is metal kind of bonding, and we got the titanium within only 7 seconds, and the strength right in this interval. On the other hand, when we use standard SPS joining process, it took around 45 minutes, and at the interlayer we got the max phase silicide. One is missing, titanium carbide as well. So you see the clear difference, and the strength of the joint was much lower. So we believe that, or I believe, I convince you that this flash joining is very interesting technique, and of course it requires further development, but we are still trying, and we are still trying to improve especially reliability of the process. So here is just a summary. So I would like just few points. I would like you to remember that in case of the joining of monolithic CVD silicon carbide, I would like to say that direct bonding, it's possible. You don't need to use any metal interlayer, but you need really high temperature and high temperature and pressure, and also you need a polished surface. In case of you use titanium, so you want to use a metal based alloys, then you can do it at 1700 or 1650, but you will have significant shrinkage and interaction with the matrix. If you use max phase, and in terms of the precenter fold, you have no shrinkage, no reaction, and you can join at the temperature as low as 1300. In case of the composite, I would like to just point out the ductility of the max phase, which can conform very well because surface of composite is very rough, so the foil can really conform very well, and you can get a nice strength. In terms of flash joining, within a very rapid heating and only whole process only 7 seconds, and you get very nice joint. That was all from my side. I would like to thank you very much once again to YCN for giving me this chance to summarize this result, and to all of you for attending this webinar. And just in case some of you are interested in this topic, then here are my contacts. You can just drop me an email and we can discuss. You can ask me whatever you want, or we can do some collaboration. Here, actually, these are 5 papers which were published in a Journal of European Ceramic Society in the last couple of years. And here you can find also more information about joining. And as a last point, I would like to also point out that recently my colleagues from Politecnico di Torino, they established a new research center, which is fully focused on advanced joining technologies. So if you are interested in joining of ceramics and also joining ceramics and metals, make sure you visit their website, and there is also a virtual tour. So you can have a look, and we will be more than happy to answer any of your questions or start new collaboration. Thank you very much once again for listening.
Dear Tatarko, thank you for your nice presentation on and interesting topic. And now go on with Burak. After the Burak's presentation, we will take the questions. Burak is one of my colleagues from my institute in Turkey. He's a material science too. He's a master's degree also.
Sorry for the delay at first. Hello, dear participants. This is Burak from Tubitak Research Center. And today I'd like to tell you about a part of my master's study. And the study intended to produce an effective material that will enable a superior photoluminescence property by using the particles with co-doped and the tridopant of the materials. In this work, ytterbium, erbium, and the thulium rare earth ions doped with the lanthan titanates, phosphors, and they were synthesized by the solid state reaction method. In the presentation, I begin with the brief information on luminescence materials and their properties. After summarizing the luminescence phenomena, I will talk about the experimental studies and their results as well. So let's begin with what is the luminescence materials. A phosphor or luminescence materials consist of a host material like oxides, nitrides, and an activator ions, which could be a transition metal or rare earth ions. These are weakly interacting with each other, and these rare earth ions act as luminescence centers in here. And the phosphors have property of being able to absorb light of one wavelength and emit at another, usually a longer wavelength. One of the most significant properties of the rare earth ions is photoluminescence of different colors in the visible and the near infrared regions. And ytterbium is the significant one here because it has larger absorption cross-section than the other rare earth ions, and ytterbium can transfer its energy to the other ions. That's why ytterbium co-doped with the other ions such as holmium or erbium, so as to enhance the emissions. In our study, we picked the lanthan titanites as a host material because it has wide band gap and it can consider as a successful host material and appropriate for doping with the rare earth ions. And lanthan titanite is a member of the family of oxide with a cubic structure of perovskite, and it is found to exhibit strong piezoelectric and electro-optic effects, and it has also extremely high Curie temperature at around 1500 Celsius. At the room temperature, lanthan titanite has a structure of monoclinic, and at around 800 Celsius, it becomes to orthorhombic. But when it reaches to the Curie temperature, it transforms to a paraelectric phase. So let's talk about the optical part of the study briefly. The luminescence, what is the luminescence? Luminescence is emission of light by a substance not resulting from a heat, but it comes from a cold body radiation. Fluorescence and phosphorescence are alike in that excitation is brought about by absorption of the photons. As a consequence, the two phenomena are often referred as the one more general term, which is photoluminescence. But the difference in here between these two, if the emission disappears when the light source is off, let's say a laser beam in our case, it's fluorescence, whereas the phosphorescence can store that absorbed light and emit for a while longer. So the photoluminescence is a process in which a molecule absorbs a photon in the visible region and exciting one of its electrons to higher electronic states, then radiates a photon when the electron returns to that lower energy states. In order to do that, we need to have unfilled electron shell structure. That's why the rare earth ions are suitable for this process. And there are three basic steps for this process: excitation, relaxation, and emission. If the energy of emitted light is lower than the energy of the absorbed light, then the process known as down conversion. Here we can see the left side. And the up conversion is the conversion of the low energy photons to high energy emissions. And the process which two or more low energy at the longer wavelength photons are converted into one high energy photon at the shorter wavelength, which is visible in the visible regions. Well, after some introduction, let's proceed with the materials and methods section. We carried out the preparation stage as follows. We used lanthan and titanium oxide as the starting materials. Rare earth ions such as ytterbium, erbium, and thulium doped with the appropriate stoichiometry in the site of lanthanum. We have succeeded producing with the conventional basic solid state methods. First, we doped powders were mixed, and then ball milling process was carried out, followed by the calcination at around 200 Celsius and sintering at 1350 Celsius applied to the powders for over 20 hours to get the structure, and optical measurements of the prepared powders were made after the characterization analysis such as XRD and SAM. So let's take a look at our results, some of our results. In the compound of lanthan titanites, due to the ionic radius close to each other, ytterbium, erbium co-activated inside of lanthanum in here. Also, we have undoped phosphors measured and showed in the XRD diffraction in order to compare with the doped substances. As we can see from the graphs, the entire product samples display a singular phase orthorhombic structure without having signs of impurities, and there is an absolute corresponding fitting with the reference cards, and there were no extra peaks were noticed. And this points out that the ytterbium and the erbium doping does not result in any second phase formation and fully dissolves in the lattice with the substitutional solid solution. But the most significant notification is to be made that a detailed examination of the peaks reveals a presence of slight shifts in the peak position to each side, left and right, with the increase of doping concentration. These shifts were noticed during the calculation of lattice parameters and the volume of the unit cell, as we can see from the tables and figures. In comparison with the undoped, co-doped phosphors showed bigger unit volume, since the addition of the rare earth ions into the crystal structure, which leads to the increase in the values of the lattice parameters as well. But there was no simple pattern between the volume and the doping concentration. I mean, volume did not increase steadily with the rising doping rate. In here, it's erbium, of course, but thus it leads to slightly distortion in the lattice. So similar cases took place in the tri-dope samples as well. In here, we fixed the ytterbium and the erbium concentration, while the thulium concentration was changing. We wanted to show how the thulium concentration affects the optical results. And also, again, there were some slight shifts between the samples in the lattice parameters, but these results showed that the tridopants also can form a solid solution in the lanthanide phosphorus. So after the XRD measurements, SAM and EDS analysis were made. Here we can see two examples: the backscattered electrons micrographs and the EDS analysis of undoped and the co-doped sample. Some micrographs reveal that there is no second phases or impurity in the microstructure, as we observed in the XRD as well, which they can confirm each other, I think. The backscattered electrons do not show any phase contrast, indicating no any other second phases. And besides from that, grain sizes are calculated via the Scherer equation, and the result was, in average, it was 50 nanometers. And you can see from the graphs that there are some spherical but mostly shapeless particle structures observed in here. Also, there's no big difference between the calculated weights and the outcomes, as we can see from the tables. And I think it can be deduced from some images that there is an agglomeration in this structure. Let's go to the next one. After the characterizational analysis, let's proceed with the optical outputs. The luminescence analysis of phosphorus single-doped, co-doped, and tri-doped in the range of 400 and around 800 nanometers under the laser excitation, which is our excitation source, for the constant power, which is it's a single pumping power here. And here we see the cases where the ytterbium, erbium, and thulium of all the dopants are together and comparatively. As we can see from the figure, is ytterbium in here is the responsible for blue and the red emission by itself. But if it's co-doped with erbium, we can see that it transfers its energy to erbium, act as a sensitizer, and erbium is the activator in here, transfer its energy to the erbium, and the blue peak that comes from the ytterbium disappears in the end. And the erbium is dominant and responsible for the green emission when it's co-doped. Similar cases occurred in the thulium ytterbium sample as well. The green emission that comes from the thulium in here, not from the ytterbium, and we can see it's changing the we can see the ytterbium transfer its energy to thulium again. How can we know that? Because as you can take a look at the camera images right side of the graph, there is a big difference between the tone of the colors. The ytterbium has the more turquoise blue, whereas the thulium has more purplish blue. So when it's tri-doped, we can all see the peaks that we observed from the co-doped cases as well. And in the tri-doped, erbium again is dominant here, and the emission is green colored. And Besides from the spectral outputs of the crystal powders, which figures also illustrate the results of the camera images, and it can also do spectral measurements at the right side of the graphs, resulted which was taken by the illuminescence meter, and it can be noticed that two spectrum results matches with each other in terms of the position of the peaks of the colors. In the previous slide, we saw how the types of the dopants and the concentrations affects the optical results and the intensities. Now let's see how a single sample behaves spectrally at the different laser powers, with the different pumping power. It can be noticed from the figure that it's the same sample. It can be noticed from the figures that the power, as the power increases, the intensity of the color emissions first increases and then began to reduce slowly. And when it's completely absorbed, then we see the intensities of the graphs is increases linearly at last. When this happens, the green emission in here, which is erbium in this case, green emission transforms to white color. And this behavior was seen on every sample of ours. So in addition to the previous slide, here we see the change in the color coordinates of the samples depending on the power. The measurements made with the illuminescence meters, we see the changes in the coordinates. At first, according to the doping ions, the samples emit blue or green color. But as we increase the laser power, we see the color coordinate changes and the color also changes to yellowish white color in every single samples. As a result, we saw the color changes. The reason behind this is thought to be the energy transfer mechanism between the ions. So as to evaluate the outcomes in terms of temperature and the rendering index, in here the Kelvin unit express the tone of the lights, and we can say that as you can see at the low power samples shows higher temperatures, which means it means it's a cool light, as we can see from the reference in here. So but with the rising of the power, usually reaches to the white light at about 1900 Kelvin. So warm colors and the cold colors, cold lights and the warm lights also could be used in the industry or home environment. To sum up, as a result of our experiment, lanthan titanite structure was orthorhombic, and after the XRD investigations indicated that there were no second phase observed in the samples, and also the grain sizes are calculated as the 50 nanometers in average via the Scherer equation. The SAM micrographs affirmed the arrangement of the single phase in the microstructure. Mostly irregular shapes were observed. So these phosphors can be used as the warm and the cold light sources and can be served for industrial and the home environments. Actually, there are some products in the market right now, but they have a different system. They have a switch system. They use as the two different colors, let's say white and blue, and they can change the colors with the switch system. But here, as a result, according to our results, we can change the color by changing the powers. So it's different from the one in the market right now. Also, it can be also used in the photovoltaic devices, because photovoltaic devices works with the upconversion materials because of their ability to absorb the lights from the low energy and convert to higher energy. And this is all by me. Thank you for giving me the opportunity to sharing my experiences and studies with you. Thank you to Young Scientists Ceramic Network again.
Jasmine, I think, are you in charge of the question session?
Thank you for your nice presentation, Burak. Does anyone wants to ask question? Firstly, Peter, and then Burak.
Maybe I can start with a question to Peter. That was a very nice presentation, and I really like this sort of a new way to do the joining without the graphite dye. So this flash, I don't know, call it the flash.
Flash SPS joining, yeah.
Flash SPS joining, yeah. So one for today's case. So what's this actually? Yeah, like even in in industrial context. Like, because you don't have the graphite dye, then you could put like large pieces, and then you would just join the piece. Then you just limit it only by the vacuum chamber size, right?
I'm sorry, I cannot hear you properly. I don't know if anyone else has the same problem.
So maybe Erka, you can stop your video and ask again.
Okay, can you hear me better now?
Erka, yeah, Erka, I'm very sorry, but I couldn't hear anything. So it was really interrupted. There was some signal problem or something.
Okay, sorry about that. Can you hear me now better?
Yes,
yeah, now
it's
clear. It's clear, yeah.
Okay, so again, like I said, very nice sort of a technique, this flash joining. Could you really, like you showed the industrial applications, so they are quite big, so like the space applications and so forth. So could this actually allow you to do this industrially? Like you need only to increase the size of the vacuum chamber, right?
Yeah.
And you could do bigger. Yeah, go ahead.
Yeah. Actually, it's a very good question. Actually, what we, if I'm not mistaken, we were at least we published as a first team this kind of work on. We wanted to show the direct effect of the electric current on joining. So what I would like to say, we used SPS, but it's not mandatory. If you have any power supply and you just really connect, you have a power supply, you connect your pieces to be joined, and you don't really need SPS. So from that point of view, I can imagine, and we are trying to, with my colleague Professor Salvatore Grasso, we are still trying to developing new technique and how to weigh. So we want to avoid using SPS for one simple reason, and this is because our SPS cannot really reliably control the power. So as I said during my presentation, we could only set a power limit in terms of percentage, which is not really, we need a proper power supply, which we will be able to say, for example, 340 amperes, and let's put in across the sample and let's see what happens. So from that point of view, but one drawback is And we need to really realize that we can only use this technique for really flat surfaces. Yeah. So if you have like a tubes or more complicated, so that's why, as I showed, for example, that European project which I was involved in, there were 7 partners, and this was one of the activities. So, for example, for more complex shaping, we were using like solders, we were using like glues, epoxy for joining. So for this kind of more complex structures, then of course not. So we need to really be clear that this technique can be only used when sample size and sample design allows.
I fully understand, but I think it's a big progress already. If you get rid of this the graphite dye, then you're less limited by the by the whole process, I would say.
Yeah. Thank you.
Yeah. Is there any question for Peter?
You can see the questions from Nicolas in the chat.
Yeah, it's for Burak. Are you planning to shape your powder for some specific application? I mean, specific shapes.
Hello, thank you for the question. Actually, we carried out our experiments with the different fields. We used my material, lanthan titanite, with electromagnetic applications right now, and we make a composite. We try to make a composite material with the polyaniline to our materials, and right now we are taking the electromagnetic fields measurements, and if the results works out, I think will be a great addition to radar absorbing materials technology. And about the shape question, our material is like very like floor. It's hard to be stand together. We need adhesive bonding to get a shape. Right now, we try to take a measurement of dielectric properties of our materials, but we try to apply a little pellets with the hot pellets and hot plates, but we need to take a look at how the adhesive bonding works with our materials right now. So I hope this
okay. Yeah, thank you. Is there any question? Both of them. Question for Peter. During the FSPS joining, what pressure is applied? I miss it. Moreover, is the joining possible without any pressure applied?
Can you? Okay, sorry. Thank you very much. Thank you very much for the question. So for the flash SPS joining, we only applied the minimum pressure which was required, or just to be in contact with the sample. So if you use a SPS, you have your joining assembly, so you need to have a proper contact. So if we are talking about numbers, it was around 7 megapascal only. So you can imagine. So there is a little pressure, but not much. For standard SPS joining, if you remember, I showed we used 50 megapascal. In terms of standard SPS joining, what I would like to say, because your second part of the question is whether it is possible. It depends on the joining technique, or better say joining filler. If you, for example, for direct bonding, in case you are not using any interlayer, it's not possible. At least not for silicon carbide. We tried our best, but even we couldn't really do it. But for example, for titanium, if we operate about the melting point of titanium, so about 1600, then very again minimal pressure, because in SPS you always need to have some pressure. So it's around 5-7 megapascal, if I remember well. So very limited pressure is always required for the SPS. But for example, if we're talking about joining with max phase, then even this kind of pressure was not successful, and we had to increase this pressure to 50 megapascals. So I hope I answered your question.
Thank you for answer, Peter.
Thank
Is
you.
there any question more? I think there is no.
Thank you very much.
Thank you.
I have a question for you, Professor Tatarko. Well, I think it's really interesting the topic you are talking about, go out from the SPS, because as you're explaining, has some limitation, and you are looking for other technologies, no? Which I am not an expertise in this topic, but which are the challenges you are facing to go out from the SPS?
Pardon me, I couldn't.
Yes, in this European project, you
Yeah.
explain us that you are trying to apply other technologies different from the SPAs. And I suppose go out from this technology has some challenge. You are facing some challenge. And I am curious about.
There were different technologies. Really, for today's webinar, I selected this electric field joining. But for example, this was mainly for MT Aerospace, for our project partners. But we had also project partners Airbus, Defense and Space. And for example, just they had completely different requirements. So for example, for their case, we were working on the satellite. So they were having the like a base, we can call it like a motherboard in a computer. So it was like a motherboard of satellite made of silicon carbide, and they needed to have very small inward alloys. It needed to be joined to the surface of silicon carbide. And for example, for that case, we were using only soldering or standard epoxy joining. So what I want to say, so for that, in that case, we put one piece, second piece, we sprayed some solder, or we sprayed some, we covered surface to be joined by some epoxy, and then we just joined. So it was very, you can do it very clearly anywhere else. So that's what I'm saying. So all these different cases, they have some difficulties or drawbacks, and we needed to solve them by adjusting the limitation. So always what the problem is, the project, for example, ended up with some demonstrators, and that kind of demonstrators were made, but just for people to imagine that we are talking about joining which could be done at room temperature or up to 200 degrees C. Here I was talking about joining at 2000 and high pressure. So it's really different situation. But in terms of this adhesive joining, for that, demonstrators were made, and they are being tested by Airbus Group. So we are a bit further than in terms of this high temperature electric field joining.
Okay, thank you so much. You are, I think you are developing a very nice project.
Trying our best, yeah. Thank you very much.
Maybe somebody else has to take the opportunity to ask.
Is there anyone?
Okay, if nobody else want to ask, I don't know, Jasmine, if you want to say something else.
Thank you for nice presentations, all of you, Peter and Burak. Let's say this.
Okay, thank you.
Thank you.
From the ICN, we want also thanks to you, Jasmine, for the effort that you put organizing this webinar. Also,
it's a pleasure for me. Thank you.
Also to Professor Tatarko for accepting the invitation very quick, and to Burak also for the nice presentation he prepared. And just I want to steal you a couple of minutes more. If Veronique, you can leave me share just the next announce. Okay. So, just to finish, we want to announce the next webinar will be in February, 16th of February. The plenary speaker will be Professor Alicia Duran, is the current president of the International Commission of Glass, and she will talk about the project they are developing towards an International Year of Glass in 2022. So if you want to join us in February, we'll be very, very happy. And that is all. Thank you so much to everybody.